Hi, this is Dr. Remenacker. In this particular video, we're going to look at several basic nonlinear functions. The term nonlinear means that they are not linear. In other words, they aren't straight lines. As you can see in the first graph provided in the upper left, that's what a linear function looks like. We've worked with those earlier. You need to be familiar with a variety of different shapes of graphs because what can wind up happening is you can be given a set of data, and I'll draw something over to the right-hand side. And if the data behaves something like this, you need to be able to take that data and convert it to an equation. Now, there are techniques on your calculator that will allow you to do this, and we'll take a look at those later in another video. But for right now, you need to be able to look at this data and realize what type of a function best fits this data. If you don't have an idea that, this looks kind of like a parabola. Oh, a parabola is a quadratic. Then you have no hope of choosing the correct equation to fit the data. On your calculator, if you have data like this and you ask it to compute a linear equation, it'll gladly compute a linear equation. It'll go something like this. But that's not going to fit that data very well. So we need to be able to identify what the basic shape is best suited to match as far as a function. If you have something that goes like this, that's not a quadratic. That could be a square root or something of that nature. We'll take a look through the various functions and you'll see sometimes there's more than one type of function that will fit somewhat well a set of data. And what we'll wind up needing to do as we move into that section where we're actually fitting equations to data, we'll have to try several different functions in some cases and see which one works best. For right now, what I want to do is take a look at not the linear function, which is in the upper left, but working with the nonlinear functions. The first of which that we're going to look at is a quadratic function. A quadratic has the shape of a parabola when it's graphed. Now with a quadratic function, you can have three different situations happen. You can have, as you see here in the upper left, a situation where the parabola never intersects the x-axis. This is a situation where you have zero real roots. In this course, we're going to restrict ourselves to just real numbers, not get into complex or imaginary numbers. A second option is the quadratic might intersect the function or the x-axis at one location only. If it intersects at one location only, this is what is called a single root. I have double down there. We'll fix this. One root. It is a double root. Okay. It's referred to as a double root because you wind up with the same solution twice. We'll see that later as we go. The third situation you can run into is on this function here, where the quadratic actually intersects the x-axis in two locations. You have two roots. So if we run into a set of data that has a shape of a parabola, whether it opens up or down, okay, it can be above or below the x-axis, we're going to want to try to fit that to a quadratic. That'll be one of the options. A different function that comes into play is a cubic. Now the cubic, it can have two basic looks to it. The first of these two looks is a situation where the function either is increasing or decreasing. It levels off and then continues to increase or decrease. A second situation is like what you see at the far right here, where it can increase, decrease, then increase. Of course, it can also do the opposite of that. It can decrease, increase, and decrease. Okay, but if you see behaviors that look like this, the function best suited to match this data is a cubic. Continuing on down, you might have a situation that looks like the one on the far left here, okay, where it increases rapidly at first, then levels off but this is very important, it never decreases. A function that will match that is a square root function. Okay? If you have a function that is V-shaped, or a set of data that is V-shaped, the absolute value will fit that data well, as you can see with this next function here, where we have essentially a V-shaped graph. That's the result of an absolute value. It's quite common for sales of products to be seasonal. Okay. In Cincinnati, for example, there's not a whole lot of suntan lotion sold in February, except for people going to Florida. Okay. There are some things that have high sales at one time in the year and low or no sales at all at another point in the year. So you get these wave-like behaviors of the number of sales. Two functions that will produce a wave-like behavior are either the sine function or the cosine function. Either of these is well suited to matching sales or behaviors that are seasonal. Moving down a little further here, hopefully moving down a little further here, we come up with a graph that starts out low and then increases. And as it goes to the right, it gets steeper and steeper. This is an exponential function. The function that matches this is y equals e to the x. These functions can also behave in a situation where they start out really high and then they run asymptotic to the x-axis as you move toward infinity. Typically, our behaviors will probably be more like this. Another function that you can run into is one where it increases, but unlike the exponential function, which gets steeper and steeper as you move to the right, this function tends to level out somewhat as you move to the right. Another thing that's important to notice is that this function runs asymptotic to the y-axis. This is a natural log function. These are quite prevalent as well with data. The last basic function that we're going to consider is the function y equals 1 over x. This is a type of rational function meaning that you have some polynomial in the denominator. And recall that y equals 1 over x actually does have a polynomial of sorts in the denominator. It's just the function y equals x. In this case, the domain prevents you from using the value x equals 0. We're going to work a little more with domains as we move forward. If you tried to put in x equals 0, the function would be undefined. This is why the function on both sides of the y-axis runs asymptotic to the y-axis, because as you get closer and closer to x, the function is either headed to negative infinity or to positive infinity. Let's take a look at a few of these different functions. First, let's look at quadratic functions. With a quadratic function, recall that you can have one of three situations. You can have a situation where the function can intersect the y-axis, but it never touches the x-axis. In this case, it has no roots. No roots in the real numbers, that is. Now, to the far right here, recall that you have the quadratic formula. You should be somewhat familiar with this. And the quadratic formula is basically negative b plus or minus the square root of b squared minus 4ac all over 2a. The part of the function or formula that is inside of the square root is referred to as the determinant. This will actually determine how many roots this particular function that you're considering, the quadratic that you're considering, is going to have. In the case where b squared minus 4ac is less than 0, remember you can't take the square root of a negative number, okay? It's undefined and you have no roots. In other words, the x value is undefined in the real numbers. A second situation that can happen is you'll have some kind of a parabola. It can either be opening up or down, and it intersects or touches the x-axis at just one location. This is going to be a case where this b squared minus 4ac is exactly equal to 0. Notice if you plug 0 in to the square root, you're going to get a negative b plus or minus 0 over 2a, and this is going to give us one value out, one root. Okay, so this would be like the second case where you have one root. A third situation that can happen is you have a parabola and it intersects the x-axis at two locations. And this will be the case where the b squared minus the 4ac is strictly greater than 0, and this will give us two roots. The root can either be positive or negative, and the positive or negative comes from looking at the quadratic formula. You have a negative b, and if you have a negative b minus some value, clearly you're going to come up with something that's negative. So the x value can wind up either being positive or negative. That is not decided by the value of the determinant, other than the fact that it has to be greater than 0. One of the things that I would strongly encourage you to do is to look up a video on YouTube and program your calculator to have the quadratic formula in it. That is going to be very important. It's going to be a huge time saver for you throughout this course and courses in the future. Yes, you can always type in the quadratic formula every time, but if you have a program in, it'll run the quadratic formula for you, and all you will have to do then is to, let's say you have something like y is equal to 3x squared plus 20x plus 3. All you would have to do, let's make this plus 4 so we have three different values. All you would have to do in this case would be to plug in the value for a, which is the x squared term, the value for b, which is the x term, and the value for c, which is your constant. And it's a whole lot easier to just plug in 3, 20, and 4, and press enter and have it return values than trying to work out all these computations using the quadratic formula. A next type of function that we're going to consider are polynomials. Polynomials are always going to be continuous functions. This is going to be very important as we move into the calculus portions of the course. Continuous, that means they don't have any breaks in them. In a book, and typically in any publication, whether it be a manuscript or whatever, you will see polynomials in general written as a sub n, x to the n plus a n minus 1, x to the n minus 1, all the way over to here where we get down to a sub 1, x to the first power, a sub 0, x to the 0 power. Now at this point I have x to the 0 written in. But recall, any number to the 0 power is really just 1. So what I have here is a sub 0 times 1. When you see this published, the x raised to the 0 power will not be there because the publishers will have assumed that you realize that the last term does have x, but it's x raised to the 0 power, which is just 1, and we don't bother with that. With polynomials, when you go to graph those, they're going to be things that do stuff like this. Okay. A couple of examples of polynomials would be something like 4x cubed minus 8x plus 7. Notice the highest power of x is a 3, or x cubed. This tells us that the degree of this polynomial is 3. It's going to be important to be able to identify what the degree is. And the degree is just the highest power of the polynomial. Notice in this case, there is not an x squared term. There actually is it would fit in right here, but it's really 0 times x squared. With a coefficient of 0, the x squared is going to zero out. So realize that even though it doesn't appear in the polynomial as it's written, it's understood to be there. It's plus 0x squared. Now, sometimes people say, well, couldn't I use minus 0x squared? And the answer is sure. If you want to add 0 or subtract 0, you get the same thing. Okay, so we're going to be taking a look at polynomials. They are continuous. They have no breaks in them. We're also going to be taking a look at rational functions. Now, rational functions refers to functions that are actually in the form of a fraction. A rational function has a polynomial in the numerator, as well as some type of a polynomial in the denominator. When you are considering a rational function, you're going to want to determine what its domain is. The domain is very important to identify. The domain talks about what values of x are you allowed to use and what values of x are you not allowed to use. To compute the domain, what you want to do is you want to look at the denominator and say, okay, where does this denominator equal 0? In this case, it equals 0 at -7. This then allows us to determine that our domain can be any x value except this -7. If we plug in -7, we'll get a 0 in the denominator, which makes the function undefined. So in this case, the domain is going to be the set of x values such that they go from -infinity to -7. Notice I'm using a parentheses here, not a bracket. We cannot include the -7. Unite this with starting on the other side of -7 over to positive infinity. So the domain of this particular function would be from -infinity to -7, union with -7 to infinity. And remember, by having the parentheses and not the bracket, we are not allowed to use or include the value x equals -7. If we were to graph this particular function, okay, and we're going to talk more about graphing functions as we move further into the course. At -7, we have a vertical asymptote. Okay. Now, for this particular rational function, notice that the degree of the numerator is 2 and the degree of the denominator is 1. Remember, this is x raised to the first power. If the numerator is 1 degree higher than the denominator, you get something called a slant asymptote. A slant asymptote is an asymptote that comes along at an angle. It's not a situation where it's either vertical or horizontal. Some of you may have seen these before, some of you may not. In either case, we're going to work with these later. Okay? The actual graph of this function works out to be something like this. Well, it's actually going to run asymptotic to that slant asymptote and come down. On the other side, notice that we have two roots. The roots occur where the numerator, this 2x squared plus 4x equals 0. This actually gives us 2x times x plus 2 equals 0, which then gives us roots at x is equal to 0, or the x plus 2 equals 0 gives us a value of -2. You do not want to go dividing by x. Okay? Sometimes people will, at this point, divide by 2 and divide by x. If you divide by x, you've eliminated one of your roots because you're just left with x plus 2. Secondly, if you're actually dividing by x, that root has a value of 0, and you're not allowed to divide by 0. Okay? So what winds up happening for this particular function is it has an intercept of the x-axis at 0, and I'm back over at the graph now, and at -2. So this other portion of the graph is going to do something like this and run asymptotic to that slant asymptote. We'll work further with graphing rational functions, but for right now, at least you've seen how do you get the roots, how do you get the vertical asymptote, and I've made mention that slant asymptotes occurred. I didn't exactly talk about how do you compute those for right now. There is one last thing that I want to mention here while are still on rational functions. We'll encounter this discussion a number of times because it's one that doesn't stick with people very well. And it's the idea of, and I'm over to the right-hand side below the graph, if you have something like 12 over 0, what does this equal? Does this equal 0 or is it undefined? And people get confused and they're not quite sure what answer to give. Okay, if you try it on your calculator, pause this video quick like, and on your calculator put in 12 divided by 0, see what you get. You should wind up with an error. Now, the reason there is an error is the following. Suppose we had 12 divided by 3. Well, 12 divided by 3 gives us 4. Okay. Running this the other direction, this says that 4 times 3 will give you 12. Okay, so that makes good sense because we know that 4 times 3 is 12. What happens if we plug in 0? Now the question is, what number over here times 0 is going to give us 12? Well, you know as well as I do that there's nothing times 0 that will give us 12, which means that this is actually undefined or does not exist. As we move through the course, it is a perfectly legit answer to say something does not exist, because there are times where the solution doesn't exist. And if it doesn't exist, you need to state such. Okay? And there are problems in the real world where there is no solution, given the conditions that you're working under. Now, if you wind up with a no solution situation in the real world, that means you need to go back and reconsider your parameters and change some parameter to get to a situation where you can actually get a solution. But remember, anything divided by 0 does not exist. Okay, let's take a look at one last thing here in this portion or in this video. You have a lot of situations where two things are inversely proportional. As one gets larger, the other gets smaller. For example, your use of gasoline. As the price gets bigger, do you use more or less gasoline? Well, you use less. Okay, so there's a quick example of something that's inversely proportional. Typically, in any case, as the price goes up, you use or have less of whatever that item is. Okay, and there gets to be a point where the price is so high that you buy 0 of them. For example, how many of you drive a Ferrari? Probably none of you. And the reason isn't because you wouldn't like to have one, it's because the price is too high. Let's take a look at an example of an inverse proportionality. They're actually fairly easy situations to solve. Okay, the problem here says the number of tickets sold to a concert is inversely proportional to the price, which makes sense. Okay, if a band was coming to town that you wanted to see and the tickets were 20 bucks, you'd probably go. If the tickets were $18,000 a piece, odds are you're not going to be there. Okay, and if they're $18,000 a piece, the odds are there are going to be a lot of empty seats there. Okay, so realize that number sold is inversely proportional to the price. To express that something is inversely proportional, we're going to use the equation y equals k over x, where k is the constant of proportionality. K allows us to adjust the relationship between the number sold and the price for this particular situation. Okay, Let's take a look at the information we're given in our problem statement. When the ticket price is 15, you sell 8,000 tickets. We need to identify which of these is X and which is Y. Is the ticket price X and the number of tickets sold Y, or is the ticket price Y and the number of tickets sold X? An important thing to remember here is X controls Y. Well, does the ticket price control the number of tickets sold, or does the number of tickets sold control the ticket price? Typically, it's going to be the ticket price controls the number sold. So typically, it's going to be price controls the number sold, which means our price is going to be X and the number sold is going to be Y. So I can come up here and I can put down my X value and my Y value, where my X value is going to be the 15 and the number sold is going to be the 8,000. You've got to be careful when you're looking at a set of data, a table of data, because people will often assume that the first column is the X value and the second column is the Y value. That's not always the case. If the person creating the table doesn't know about independent variables, X, independent variables, Y, they may create the table with the Y values listed first and then the X values, but you need to be on your toes and realize, this is set up backwards. Okay, so we have some information here. X is 15, Y is 8,000. We can plug these values or substitute these values into our equation and use this then to compute our value for K. K is going to work out to be this 8,000 times 15. And if you work that out, that works out to be 120,000. Okay, so with that information, that gives us our equation Y is equal to 120,000 over X. In this particular problem, you're asked to estimate the number of tickets sold, that's the Y value, when the ticket price is $20, that's the X value. So in my table, I'm going to put my X value as 20, and what we need to do now is compute the Y value. To do that, I'm going to take my X value of 20, substitute that into my equation where I have my proportionality constant now computed. And this is going to give me that Y is equal to this 120,000 divided by 20, which gives us then, after you simplify this, 6,000. Now notice this tells us that if we raise the concert ticket price to $20, we're going to sell 6,000. This is to be expected, and it's the way consumers typically behave. At $15 a ticket, they bought 8,000. At $20 a ticket, they buy less tickets, 6,000 of them. Okay, so the behavior does match what we would expect to see in the real world. When you're dealing with inverse proportionalities, you want to be aware that you need to use this equation y equals k over x. You're going to have some initial data that will allow you to compute y or k. It'll allow you to compute your constant of proportionality. Okay, and you can then create a new equation like we did over here using this constant. And then from that, estimate what our ticket sales are going to be at a different price.